On page 204 of the textbook, number 33, which is a combination of conservation of momentum and conservation of energy. It says a 1.0 times 10 to the third kilogram Toyota collides into the rear end of a 2.2 times 10 to the third kilogram Cadillac stopped at a red light. The bumper's locked, the brakes are locked, and the two cars skid forward 2.8 meters before stopping. The police officer, knowing that the coefficient of kinetic friction between tires and road is 0.4, calculates the speed of the Toyota at impact. What was that speed? Okay, so here we have a 1,000 kilogram Toyota is moving at some speed which is unknown. We'll call that V1. And it crashes into a Toyota or a Cadillac that's 2,200 kilograms, which was not moving. Okay, so V2 equals 0. And then afterwards, they're stuck together. So it's like one big mass of 3,200 kilograms moving in this direction. And it skids a distance of 2.8 meters. So it ends up, over here somewhere. After skidding a distance of 2.8 meters. And they also tell us that the coefficient of kinetic friction is 0.4. So this is a perfect example of conservation of momentum and conservation of energy. We know it's conservation of momentum because there's a collision involved, and there's going to need to be conservation of energy too, because after the collision, the cars are going to skid and eventually stop. So they lose their kinetic energy due to friction. Okay, so I'm going to start out by using my momentum equation. It's P before equals P after. So, before the collision, I have two separate objects. So to find the total momentum, I add the momentum of each object separately. Afterward, I have one object, basically, moving at one speed. So there's the equation that I would use. Ultimately, I'm trying to find V1, which is the speed of the Toyota. So if I want to solve for V1, first of all, N2V2 is 0 because the Cadillac was at rest before the collision. So all I have is N1V1 equals N1 plus N2 times V. And then I'll solve for V1 by dividing by N1 on both sides. And now I have an expression for V1. The problem is, I don't know what that V is. V is the speed of the two cars, their mutual speed after the collision. And I can't find that yet. I need to use conservation of energy for that. So I'm going to write out the law of conservation of energy. Work non-conservative plus PE initial plus KE initial equals PE final plus KE final. Okay. Now, the cars are on level ground both before and after the collision, so there is no change in potential energy. So I'm going to cross that out. Okay. After the cars skid to a halt, they have no kinetic energy. So the right side of this equation is 0. And the left side is going to be 1/2 times the mass, velocity squared, plus work done by friction, because friction takes away all of the initial kinetic energy of this system. Okay, work done by friction is equal to frictional force times distance, cosine of 180, since it's skidding, plus 1/2 mv squared equals 0. Okay. Now, since it's on a flat surface, frictional force is equal to mu times the weight of the car, or cars, rather. So I have mu mg d, and then cosine of 180 is -1, so I'm just going to put that in the front, and then plus 1/2 mv squared equals 0. Okay, so I'm going to bring mu mg d over to the other side. 1/2 mv squared equals mu mg d. The m's will cancel. I can solve for that v by multiplying by 2 and taking the square root. So v is going to be the square root of 2 mu g d. We'll plug the numbers in. It's 2 times mu is 0.4, g is 9.8, and d is 2.8 that was given. Okay, we're getting a velocity here. 2 times 0.4 times 9.8 times 2.8. And then take the square root. I'm getting 4.69 meters per second. So that's the mutual speed of the two cars after the collision. And then what I'll do is take that and plug it into my expression above for V1. So I had V1 equals M1 plus M2 times V over M1. So we'll plug all this in. Mass 1 was 1,000 and mass 2 was 2,200. So the total is 3,200 kilograms. Their speed is 4.69 meters per second. And divided by the mass 1, which was 1,000 kilograms. I plug all that in. So I have this times 3,200 divided by 1,000. Then I get 14.99, so we'll say 15 meters per second. So that was the speed of the Toyota before impact. So it shows how we can use both conservation of energy and conservation of momentum to solve certain physical problems.